So we learned the basic idea of the multicollinearity problem. So when multiple regressors have a linear relationship, perfect linear relationship, then you cannot use them together. And then how can we tell if the data or the regression model has this problem or not? The easiest way to see the multicollinearity is to calculate the correlation between regressors. So for example, if x1 and x2 are multicollinear, their correlation is either +1 or -1. So -1 also is a problem. So when you have two regressors involved in the multicollinearity, it's easy to detect. But like this case, there may be more than two variables involved in the multicollinearity problem. In this case, the correlation coefficient is not enough to find the problem. So in this case, you have to think. So you need to think about what's the problem. But anyhow, I don't worry too much about this problem, because if there is a multicollinearity problem, then you cannot overlook that. It always shows up. So because like numerically, mathematically, a multicollinearity problem conceptually is, you can think it as a kind of calculating a over b when the denominator equals to 0. So I will not prove this, but this is how I teach doctoral students when I talk about the multicollinearity. So anyhow, so you have the computer calculate a over b, but you put 0 in b. Then you cannot ignore that problem, because the computer cannot have the answer. So your software will let you know, right? Either by crashing. So when you do calculate this, bad software will crash, will calculate forever, or will give you an error message like some problem, division by 0. Or Stata, like a more well-developed and popular program like Stata, understands this problem, so it automatically drops one of the variables. But what's dropped is chosen arbitrarily by the program. Maybe the last one you entered is dropped. So this is the solution. The treatment is this. The answer is, you cannot use these three variables at the same time. You cannot use these two variables at the same time. The only way you can use some of them is to drop one. So choose one of them, and in this case you have three variables, then choose two of them. You cannot save all three of them. So Stata knows that. So Stata will drop an arbitrary, like maybe the last variable. Then it will give you something, but the results is not what you wanted. Like something like this, you will see this kind of result dropped. It's automatically dropped. The second one is dropped automatically by Stata. Stata has built-in function in this case. So it is not so difficult to detect the problem, and the solution is also not that difficult. Drop one of them, and usually Stata does it for you. But when the model becomes more complicated, then Stata understands it, but you may not understand why one variable is dropped. But then of course you have to understand why this problem happens and why the variable is dropped as a remedy to the problem. So that's why I'm teaching this problem. And let's go back. I will give you more concrete example from here. So back to the student-teacher ratio example. And in an earlier illustration, we considered a simple division of the data into two groups, small class size group and large class size group. So the division is arbitrary, the categorization is arbitrary, which the authors chose 20, and it doesn't need to be 20, but let's for a while just use an example. As an example, I'm going to use 20. So I will define an observation is in small group, small class group, if the student to teacher ratio is 20 or smaller. Otherwise, it is 0. So the variable small is defined in this way. It takes 1 or 0 depending on this. On the other hand, large variable, another variable large is defined in a similar way, but using the other condition, the opposite case. So if the student to teacher ratio is greater than 20, strictly greater than 20, then the variable large takes 1 and 0 otherwise. Then as you can see from the definition, if small variable takes 1, so if a school district takes small equals to 1, then automatically it cannot be large. So if a school district belongs to small, then large should be 0. And vice versa. If small takes 0, then automatically the school district is in large class size group. So large is 1. This is exactly the problem we described earlier. If you know 1, then the other variable is determined. If you fix small variable at 0 or at 1, then depending on 1 or 0, the other variable is determined. And the relationship, mathematical relationship is this. Small is 1 minus large. Or small plus large is always 1. So they are the same thing. So this is the multicollinearity problem. This happens, this is the most common multicollinearity problem when you have a dummy variable. So the textbook describes this problem as the dummy variable trap. So when you use dummy variables, you have to be careful what you can include and what you have to drop, or you have to choose what to drop. So think about the full regression model, including everything you have. So including the intercept, including small variable, including the large variable. So if you include all of them, then as I said earlier, you are in trouble. It does not work. This regression model cannot be estimated because of these two regressors have multicollinearity, and as I said, they have this problem. So in this case, by the way, what you have to understand here is you have to imagine the intercept as the third regressor. So intercept is a constant. So when you have a linear relationship, when you write the linear relationship in this way, small plus large equals to 1, then this 1 is coming from the intercept. So you can think that beta 0 plus beta 1 small plus beta 2 large is actually beta 0 times 1 plus beta 1 times small plus beta 2 times large. So times 1 is hidden. So 1 is a separate regressor, an independent variable itself. So that is, including the intercept, 3 regressors together have a linear relationship. So then you need to drop one of these 3 regressors. You may drop the intercept, or you may drop one of these 2. So dropping the intercept is maybe it's a little bit less intuitive, but if you understand intercept as 1 in this relationship. So there are 3 variables involved in this relationship. So then intercept is also one of the reason you have the trouble. And as I said, these beta 1, beta 0, beta 1, beta 2 cannot be computed by the OLS method because there is no variation you can utilize. No variation to estimate the ceteris paribus effect. It is quite common. This problem is quite common. So you have to drop one of the 3 regressors. And if you drop the last one, you get this. Beta 0 intercept and small. Or if you drop the small variable, you have intercept and large. And alternatively, it is also possible that you drop the intercept and use these 2 variables at the same time. That is possible. It is a legitimate model. So you need to choose one of these 3 methods, one of the 3 models to estimate. So they are different in their interpretations. So we have to study how they differ and how can we interpret the intercepts and the coefficients in each of those models. So I will compare these 3 models in the next video. So thank you for watching, and see you in the next one.